Hi everybody, this is Mrs. Dinkelman and we're in Unit 10 talking about the series test. And today the two tests we're talking about are both comparison tests. One's direct comparison and one's limit comparison. We've done the direct comparison test. It was called the comparison theorem back when we were looking at improper integrals, and I told you it was going to be coming back. So let's just kind of fill in the blank here. My bet is if we have multiple choice tests that you will do the comparison quite quickly. You will understand why it works. It's just that we need to make sure that you can kind of follow through with all the steps and earn all your points on a free response and show that you know mathematically why the comparison works. So both of these are a sub n and b sub n are going to have to be above the axis basically, or above 0, so that we don't have any negative infinity issues. Let's see. In here, I think what I'm going to grab onto first is just what's happening here. So if we know for sure, so b sub n is a known convergent series, and we want to know about a sub n, and a is less than b. So this is kind of when I think of, oh, if b sub n converges, let's just say it's 7. So a then has to be less than 7 but greater than 0. So that means a sub n must converge. This one is just reversed, so it kept the same inequality. We want to know about b, but we happen to know that a sub n diverges, so let's say it's infinite. So now b is greater than something that's infinite, and the only thing that's greater than infinity is really infinity, which means this guy must diverge also. The hard part sometimes, again, is picking that comparison, which we ran into with the comparison theorem. What I would really want you to do on a multiple choice here is say, oh, this looks like n to the 1/2. 1 over n to the 1/2, that's a p series. And if p is less than or equal to 1, we get something that diverges. So I would hope that you would make a really quick decision on that one on a multiple choice based on that. But what we're really saying is we should really prove that that comparison works, that this thing really does act like a p series. So with the direct comparison, on this one, I'm going to show you a kind of a known mistake. So if you want to put your pencil down, I want to show you what happens if you do an incorrect comparison. Because this one seems to me, like I said, that I want to compare it to 1 over n to the 1/2. Well, let's compare using an inequality. So let's think about this one that I have and this one I want to compare to. So if I were thinking of those as functions, what I would say is this one is smaller because we're dividing by a bigger number. So less than or equal to our 1 over n to the 1/2. Well, since this is infinity, this one then is less than infinity. Well, we talked about why this is a bad comparison or a bad statement. We can't just say, oh, less than infinity, it must be infinity, because 12 is less than infinity, but so is infinity. So this is not a great comparison, and this is when I would stop and say, okay, let's find something else to compare to. Now, I'm pretty sure that this diverges based on my conversation with you earlier. So maybe we should just try to compare to 1 over n. And this is where, for me, this test gets difficult because it's hard to make that comparison. So graphing might be helpful. And if we have Desmos available, it might be the better one. But I'm going to go ahead and just do it on here because if we're taking an AP exam, we don't generally get to use Desmos. But it could be, if you are working on this, it might be a little bit better visual. It's just nice and clear that way. Okay, so there's my first one, and 1 over x. And let's just look at, I don't know what kind of window I have, but let's just look at it. We're hoping to look right up here in this area. And let's just zoom a little bit. So actually, let me change my window. So let's go -1 to 10 and -1 to 10. And maybe I should do not 10, maybe I should do 5s, and that'll just zoom it a little bit. We'll see if that's a better zoom. Okay, so it looks like to me that our 1 over x was always above, and so, oops, I didn't want it that way. Let me look again. I might have picked a bad comparison again. Let's see which one I had in order. Okay. And I'm just going to regraph that so we can look again. And it could be I need to zoom here and see if they intersect. Maybe they intersect right there, which is fine, because what I want is I really kind of want that 2 plus root n, I want that one really to be in the denominator, or to be greater eventually. So let's just look a little bit closer. Window. We're going to go out a little bit further, so let's go 15, but let's go maybe here, that'll work. We'll see. Again, you can maybe tell why this one isn't so great. So there's the one with the square root. Yes, so after a certain point, which is fine because we know that that first little bit is finite. So after a certain point, this guy ends up being greater. So, and that one's infinity, and so the one that we're talking about is greater than something that's infinite, which means it also diverges. So let me recap. We need to find something to compare it to. My recommendation, if you can't quite tell which one's greater or less, is to graph it just like we did with the comparison theorem, and just make sure that we have the right kind of comparison. Let's perhaps just take a quick peek at the ones I want you to do direct comparison with. So on this one, for instance, I think comparing it to 1 over 3 to the n, which is really the same as 1/3 to the n. So a geometric series, and deciding what that one does, and doing your inequality that way. Because again, the denominator of this one is bigger, so we're dividing by something bigger, which means ours should be less. Okay, so just kind of making those inequalities to determine what's happening. Okay. This next one is, for me at least, a little bit nicer as far as I don't have to have so much living up in my brain to think about the comparison. I can kind of do a procedure on paper, and sometimes that's helpful. So with limit comparison, we're still going to pick something to compare it, but the way we're going to prove that our comparison is good is by showing that the limit is finite and positive. Let's think about when we have limits where we're comparing an a sub n and a b sub n, or just two things together as n approaches infinity. So remember, this is where we get like the top heavy. I'm going to write that out a little bit further. Top heavy. Sometimes we get bottom heavy, and sometimes we get equal. Okay, so we get top heavy when, and that would be the case when A would outgrow B. So A would be bigger than B. And so those wouldn't be a good comparison because A and B don't act the same. If we got bottom heavy, which would be 0, so top heavy, bottom heavy. If we got bottom heavy and got 0, that would mean that B sub n is outgrowing A. And I don't want that to happen because, again, I want to be showing that my two things that I'm comparing really do the same thing. So when they're equal, remember, I look at the ratio of the coefficients. So this is what I'm really looking for, is this one right here. I'm looking for that to be a number, so finite and positive, because that's showing that A and B really do act the same. And since I know what one of them is doing, I can just then automatically say that's what the other one's doing. So let's go back and use that comparison I tried earlier that didn't work on that first example, but it's going to work on this one. So I'm going to go limit as n approaches infinity, and it doesn't really matter which one ends up on top because, again, whether we get 2 or whether we get 1/2, both of those are finite and positive numbers. So let's see, I'll just put the one I'm interested in here. And I'll go ahead and flip. I'll think about flipping and multiplying. What that's going to end up with is an n to the 1/2 here over 2 plus, I'm going to call this n to the 1/2. So the ratio of the coefficients here is 1. And as long as I get a positive finite number, what I'm proving to at least the person who's grading this is that I really do know that these two things should act the same. So by P series, I know this guy diverges, knew that earlier, and so now I know that my example also then diverges. And I've proved that it works because I've proved that when I take the limit of the two compared, that I get that finite positive number. Okay, so really similar in how you pick what you're comparing to, but a little bit more procedural where you show the limit. So I asked you to do 2 problems where you're doing a direct comparison. I asked you to do 2 where you're doing the limit comparison. And then after that, I'm just having you decide whichever one you want to do is fine for a comparison. So you just make that decision. I have my own personal opinion, but I want you to kind of come up with what you think makes the most sense to you.